Good morning everybody. Today I am going to present a lecture on the topic gas turbines. So let me tell you what is a gas turbine. Now a gas turbine is a machine delivering mechanical power or thrust, means which delivers mechanical work. It does this using a gaseous working fluid. So this gaseous working fluid can be any gas. Now the mechanical power generated can be used by, for example, an industrial device. Means this mechanical power which is being generated from the turbine, it can be used by any machine, industrial machine like compressor, condenser, we can say anything. Now the outgoing gaseous fluid, it can be used to generate thrust. The gaseous fluid which is coming out from the turbine, that gaseous fluid that generates the work or thrust. In the gas turbine there is a continuous flow of the working fluid. Now this working fluid, it is initially compressed in the compressor, means there is a compressor in the turbine attached to a turbine, and the work fluid is being compressed in that compressor. After that it is then heated in the combustion chamber. Finally it goes through the turbine, means after passing through the compressor and then through the condenser, it then passes through the turbine. Now what the turbine does, turbine converts the energy of the gas into mechanical work. Now part of this work, it is used to drive the compressor, and the remaining part is known as the net work of the gas turbine. Now let me tell you about the history of the gas turbines. Now we can distinguish two important types of gas turbines. There are industrial gas turbines and there are jet engine gas turbines. Now industrial gas turbines were developed rather slowly. This was because to use a gas turbine, a high initial compression is necessary. This rather troubled early engineers. Due to this, the first working gas turbine was only made in 1905 by the Frenchman Rateau. Now the first gas turbine for power generation became operational in 1939 in Switzerland. It was developed by the company Brown Boveri. Now gas turbines had a rather low thermal efficiency, point to be noted. They have low thermal efficiency, but they were still very useful. This was because they could start up rather quickly. It's very easy to start them. They were therefore used to provide power at peak loads in the electricity network. Means with the help of turbines we can produce power. Now in the 1980s, natural gas made its breakthrough as fuel. Since then the gas turbines have increased in popularity. After World War II, the gas turbine developed very rapidly, very fast. Now new high temperature materials, new cooling techniques and research in aerodynamics strongly improved the efficiency of the jet engine. This is jet engine, this is also a type of gas turbine. It therefore soon became the primary choice for many applications. Currently there are several companies producing gas turbines. The producer of both industrial gas turbines and jet engines is GE. You have already know GE is a very famous company from the USA, General Electric. Rolls-Royce and Pratt and Whitney are also important manufacturers of jet engines. Now this is an ideal gas turbine. Let me explain this gas turbine flow diagram. Now the cycle that is present, it is known as Joule-Brayton cycle. Cycle consists of 4 important points. We start at position 1, where the gas has passed through the inlet. After that the gas passes through the compressor as shown in the diagram. Now we assume that compression is performed isentropically, means at constant entropy. So we can say that S1 is equal to S2. Now the gas is then heated in the combustor at point 3. This is done isobarically, means at constant pressure. So we can say P2 is equal to P3. Finally the gas is expanded in the turbine, point 4. Now finally the gas is expanded in the turbine. This is again done isentropically at constant entropy. So we can say that S3 is equal to S4. Now the whole process is visualized in temperature entropy diagram as shown in below. Temperature entropy diagram. Now the cycle consists of an isentropic compression of gas from state 1 to state 2. A constant pressure heat addition to state 3. Now again an isentropic compression, isentropic expansion to state 4 in which work is done, and finally an isobaric closure of cycle back to state 1. Now when examining the gas turbine cycle, we do make a few assumptions. We assume that number 1, we assume that the working fluid is a perfect gas with constant specific heats Cp and Cv. Now also the specific heat ratio K is equal to Cp upon Cv is constant. Now we also assume that the kinetic oblique potential energy of the working fluid does not vary along with the gas turbine, it also remains constant. Finally, the losses which are very important, which have to be considered, the pressure losses, mechanical losses and other kinds of losses are ignored. We should ignore these losses. Next comes the classification. Now the gas turbines can be classified into two categories, that is impulse gas turbine and reaction gas turbine. Now if the entire pressure drop of the turbine occurs across the fixed blades, the design is impulse type. Means if the entire pressure drop is across the fixed blades, then the design is impulse type, while if the drop is taken place in the moving blades, the fixed blades they only serve as deflectors, the design is called as reaction turbine. Difference between design and impulse I am telling. Now the advantage of the impulse design is that there is no pressure force tending to move the wheel in the axial direction, and no special thrust balancing arrangement is required. Now there being no tendency for gas to leak over the tips of the moving blades, a purely reaction turbine is not generally used. In a small multi-stage construction, the velocity change in the moving and fixed blades is about the same, the design being 50% reaction types. Next comes the gas turbine power plant. The simple gas turbine power plant, it is shown in the next figure. This is the gas turbine power plant. They mainly consist of a gas turbine coupled to a rotary type air compressor and a combustor or a combustion chamber which is placed between the compressor and the turbine in the fuel circuit. Auxiliaries such as cooling fan, water pumps, etc. and the generator itself are also driven by the turbine. Other auxiliaries are starting device, lubrication system, duct system, etc. Even along with these things, there can be also other auxiliaries such as intercooler, a regenerator and a reheater. This is the diagram showing a gas turbine power plant. Compressor, combustion chamber, gas turbine, alternator, starting motor and auxiliaries that I have already told you, regenerator, reheater, intercooler. Now the basic construction of a gas turbine, it employs vanes or blades mounted on a shaft and enclosed in a casing. The flow of fluid through turbine in most designs is axial and tangential to the rotor. Now there are mainly two types of blades being used in the turbines, those that are fixed on the rotor and moved with the shaft, and those that are fixed to the casing and they help to guide and accelerate or decelerate the flow of fluid, which are called as vanes. Now the power of the turbine, it depends upon the size, shape and the speed of the blades which we are using. Now the multi-staging is employed to increase the power output of the turbine by placing additional sets of fixed or moving blades. Now to prevent the leakage of the gas seals are being also used. Now the extending length of the shaft on the two sides of the turbines are supported on journal bearings, which also maintain its alignment. Means with the help of the journal bearings we maintain the alignment of the extended shafts on the turbines. Now there are several accessories fitted to the turbine. There are these are tachometer, which checks the speed through a gearbox, an overspeed governor, a lubricating oil pump, and a fuel regulator. Now the starting gear, it is mounted on the shaft at one end. What tachometer does? Tachometer shows the speed of the machine, that with what speed the machine is being running, and also actuates the fuel regulator if in case the speed rises above or fall below the regulated speed, so that the fuel regulator admits less fuel or more fuel into the combustion, and it varies the turbine power according to demand of the load. Now the governor back of fuel feed, if the exhaust temperature from turbine exceeds the safe limit. Thermal switches at the turbine exhaust acting on fuel control to maintain present maximum temperature. What lubricating pump does? It supplies oil to the bearing under pressure. Other auxiliaries used on the turbine plant include the starting motor or the engine with starting gear, oil coolers, filters, and inlet and exhaust mufflers. Now the turbine is driven by the starting motor through a clutch and a gearing system. Now a standby motor driven pump is also provided for emergency service. A failure of lubricating pump system results in the stopping of the complete unit. Means if the lubricating system it gets failed, the whole system will come to a standstill. Next comes the compressor. A compressor is a device that is used to supply compressed air to the combustion chamber. The compressors are broadly classified as positive displacement type and rotodynamic type, and may be of single stage or multi-stage design. Now what happens in the positive displacement machine? The successive volumes of air, they are pressurized with a closed space. Now these may be of reciprocating type or rotary type. Now in reciprocating type machines, air is compressed by a piston in a cylinder. There is a piston cylinder arrangement, and the piston it reciprocates inside the cylinder. While in the rotary type, this is accomplished by positive action of rotating elements. Now the rotodynamic compressors, they may be of radial flow, axial flow, or mixed flow type. Now in these machines, the compression takes place by dynamic action of rotating vanes, means blades or impellers, which impart velocity and pressure to the air as it flows through the compressor. Now these rotodynamic type compressors, they include centrifugal, axial, and mixed flow compressors, which are all high speed machines running at as high as 3000 to 4000 rpm, driven by the turbine. Now these are designed to have high value of air discharge capacity at moderate pressure. These type of compressors, they are usually employed for gas turbine applications. Next comes the combustor. A combustor is a device inside which the combustion of fuel takes place. Inside, we can say inside the combustion, fuel burning takes place. Now for an efficient operation of the gas turbine, it is necessary to ensure good combustor performance. That combustor should be very efficient one for efficient operation of the turbine plant. A good combustor should achieve completeness of fuel combustion and the lowest possible pressure drop in the gas, besides being compact, reliable, and easy to control. Means the main thing is that the fuel burning should be complete inside the combustor. If fuel burning is incomplete, that will automatically affect the efficiency of the plant. Now the complete combustion of the fuel, it depends upon three factors, that is temperature, time, and turbulence. Now this temperature, it directly affects the combustion, and high temperature is conducive to the rapid combustion. Now next comes the generator. Now it is a device that generates electricity means electricity is generated with the help of the generator. It is coupled to the same shaft of turbine and runs at same speed that of turbine. Means generator is attached to the same shaft at which the turbine is being attached, and it runs again at the same speed as that of the turbine. Now, the capacity of generators depends on installed capacity of the plant. How much capacity of the plant is that on that depends upon the capacity of generator. The types of generator to be used depend upon the purpose for which electrical energy is to be produced, that whether it is for domestic use or commercial use. On the basis of that, we use the generator. Next comes the type of gas turbine power plants. Now, the gas turbine power plants, they can be classified mainly into two categories. These are open cycle gas turbine power plant and closed cycle turbine power plant. First comes the open cycle. Now, in this type of the plant, the atmospheric air is charged into the combustor. We charge air from atmosphere into the combustor through a compressor, and the exhaust of the turbine also discharges to the atmosphere. But in case of closed cycle gas turbine, the mass of air is constant, means we are using a suitable gas as a working medium, and that circulates through the cycle over and over again. That suitable gas medium, it circulates inside the turbine cycle plant. That is the difference between the two, open and closed. So, this is the diagram showing an open cycle gas power plant. In the process shown, the cycles are 2 to 3 is isentropic compression, 3 to 4 is heat addition at constant pressure, 4 to 1 is isentropic expansion, and 1 to 2 is heat rejection at constant pressure. Now, the ideal thermal efficiency is given by heat supplied minus heat rejected divided by heat supplied, where R is the compression ratio, V2 upon V3. Now, in actual operation, the processes along 2, 3 and 4.1 are never isentropic. That is, the degree of irreversibility of these processes and the mechanical efficiencies of the machines greatly reduce the ideal value of the thermal efficiency of the cycle. Efficiency of the cycle is never up to mark, it remains reduced. Now, if the air entering the combustor is preheated by the heat of the exhaust gas escaping the turbine, then some heat can be recovered, resulting into an increase in the efficiency of the cycle. Means by preheating the heat which is entering in the combustor, we are saving the energy. So, this will result in the efficiency of the cycle. Efficiency of the cycle will get improved. Now, such heating of combustor air is known as regeneration. Means by using regenerator, we can improve the efficiency of the cycle. Now, since most of the output of the turbine is consumed by the compressor, point to be noted. So, the actual efficiency of the cycle depends upon the efficient working of the cycle, compressor. If the compressor is using more heat, more energy of the turbine, naturally the efficiency will be less. And if the compressor is working properly and there is not much use of the energy from the turbine, naturally the efficiency of the cycle will increase. Now, to attain high compression ratios, it is necessary to use multi-stage compression using intercooling. Next comes the closed cycle gas turbine. This is the arrangement of closed cycle gas turbine plant. Now, in this cycle, working fluid is compressed through the requisite pressure ratio in the compressor and fed into the heater, where it is heated up to the temperature of turbine. Means we heat up to the temperature of the turbine, and the exhaust is cooled to the original temperature in the pre-cooler. Now it then re-enter the compressor to begin next cycle. Point of view is clear. So, thus the same working fluid circulates through the working parts of the system, that the same working fluid is being circulating again and again. Now, the heater burns any suitable fuel and provides heat for heating the working fluid. There is thus a great deal of flexibility in respect of furnace design and use of fuel, allowing low cost fuel to be used. Now, another advantage in use of closed cycle is the choice of selecting a convenient pressure range once the pressure ratio has been selected. Now, the volume of the air or the working fluid in the cycle depends upon the pressure range, which in turn affects the size of the air heater, compressor, turbine, etc. Now, the pre-cooler in the closed cycle plant is an important equipment and corresponds to the condenser of the steam plant. The design of the pre-cooler is commonly of the shell and tube type, and water is the coolant commonly used. Next comes the fuel which we are using for the gas turbine power plant. Natural gas is the ideal fuel for gas turbines, but this is not available everywhere. Blast furnace and producer gas may also be used for these plants. However, liquid fuels of petroleum origin such as distillate oils or residual oils are most commonly used for gas turbine power plants. The essential qualities of these fuels include proper volatility, viscosity and calorific value. At the same time, the fuel should also be free from moisture and suspended impurities, because these impurities they may clog inside the nozzles and damage the valves or plungers of the fuel pump. Now, residual oil burns with less ease than distilled oils, and the heaters are often used to start the unit from cold, after which the residual oils are read into the combustion. Now, next comes the types of gas turbines. First comes the jet engine. Now, air breathing jet engines, they are gas turbines optimized to produce thrust from the exhaust gases or from ducted fans connected to the gas turbines. Jet engines that produce thrust from the direct impulse of exhaust gases are often called turbojets, whereas those that generate thrust with the addition of ducted fan are often called turbofans or fan jets. Now, gas turbines are also used in many liquid propellant rockets. The gas turbines are used to power a turbopump to permit the use of lightweight, low pressure tanks, which saves considerable dry mass. Now, this is a diagram of a gas turbine jet engine. Turboprop engines. A turboprop engine is a type of gas turbine engine which drives an external aircraft propeller using a reduction gear. These engines they are generally used on small subsonic aircraft, but some large military and civil aircraft such as the Airbus. Now, aeroderivative gas turbines. Aeroderivatives are also used in electrical power generation due to their ability to be shut down and handle load changes more quickly than industrial machines. They are also used in the marine industry to reduce weight. Next comes the amateur gas turbine. In its most straightforward form, these are commercial turbines acquired through military surplus or scrapyard sales, then operated for display as part of the hobby of engine collecting. Next comes the auxiliary power units. Now, APUs they are small gas turbines designed to supply auxiliary power to large mobile machines such as an aircraft. What they supply? They supply compressed air for air conditioning and ventilation, compressed air startup power for larger jet engines, mechanical power to a gearbox to drive shafts or other accessories, electrical, hydraulic and other power transmission sources to consuming devices. Next comes the industrial gas turbines for power generation. Now, the industrial gas turbines differ from aeronautical designs in that the frames, bearings and blading are of heavier construction. They are also much more closely integrated with the devices. They power electric generate and the secondary energy equipment that is used to recover residual energy. Now, they range in size from manned portable mobile plants to enormous complex system weighing more than 100 tons housed in block size buildings. Next comes the turboshaft engines. Turboshaft engines are often used to drive compression trains and are used to power almost all modern helicopters. The primary shaft bearers of compressor and the high speed turbines are often referred to as the gas generators. Next comes the micro turbines. Micro turbines are one of the most promising technologies for powering hybrid electric vehicles. They range from handheld units producing less than a kilowatt to commercial sized systems that produce tens or hundreds of kilowatts. Now, the basic principle of micro turbines are they are based upon micro combustion. Micro turbine systems they have many advantages over reciprocating engine generators such as higher power to weight ratio, low emissions and they have just only one moving part. Mean to say that if the moving parts are more, naturally the friction will be more and the efficiency will be less. Micro turbines also have a further advantage of having the majority of the waste heat contained in the relatively high temperature exhaust, making it simple to capture, thus reducing the waste. Next comes the external combustion. Most gas turbines they are internal combustion engines, but it is also possible to manufacture an external combustion gas turbine, which is effectively a turbine version of a hot air engine. Now, gas turbines in surface vehicles. Now, gas turbines are often used on ships, locomotives, helicopters, tanks and to a lesser extent on cars, buses and motor vehicles. Turbocharger. The turbocharger is basically a compact and simple free shaft radial gas turbine which is driven by the piston engine exhaust gas. Now, the centripetal turbine wheel drives the centrifugal compressor wheel through a common rotating shaft. Next comes the concept cars. The first serious investigation of using a gas turbine in cars was in 1946 when two engineers Robert Kafka and Robert Engelstein of Carne Associates, a New York engineering firm, came up with the concept where a unique compact turbine engine design would provide power for a rear wheel drive car. Many cars were being developed in the year 1953, 1956 and 1959. Next come the racing cars. The first race car fitted with the turbine was in 1955 by a US Air Force group as a hobby project with a turbine loaned them by Boeing and a race car owned by Firestone Tire and Rubber Company. Next come the buses. The arrival of the capstone microturbine has led to several hybrid bus designs starting with HEV1 by AVS of Chattanooga, Tennessee in 1999 and closely followed by eBus and ISE Research in California and Design Line Corporation in New Zealand. Next come the motorcycles. The MTT turbine superbike appeared in 2000 and is the first production motorcycle powered by a turbine engine, specifically a Rolls-Royce Ellison model 250 turboshaft engine producing about 283 kilowatt. Next comes the trains. Several locomotive classes have been powered by gas turbines, the most recent incarnation being Bombardier's jet train. Next come the tanks. Now the German Army's development division studied a number of gas turbine engines for use in tanks starting in mid 1944, and the first gas turbine engine used for armored fighting vehicle GT-101 was installed